Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to lecture 3 of module 3. In the previous lectures of module 3, we discussed about the basics of surface waves. Then after we discussed about the equation for Rayleigh wave, and then we also discussed about the equation for Love wave. In the today's lecture, we will be discussing about the love waves and its characteristics, and most importantly, we will be discussing about the various modes of dispersion. So the concept that we are going to cover today will be the love waves and its dispersion, and then we will be having the summarized view of today's lecture. So what are the characteristics of the love waves? So if we go on to the characteristics, there are three basic characteristics of the love wave. First is the love wave consists of SH wave motion, as we have already discussed about it in the previous lecture. And in order for the love wave to exist, the positive velocity gradient, or you can say the positive velocity jump, is required for the love waves to exist. So if you can see, if suppose there is a layer, then the velocity of this layer V1 should be less than the velocity of the layer just beneath it. So the love wave and its SH wave motion will be basically having the bounce of motion in this particular layer and will generate the love wave. And love waves are inherently dispersive in nature. That means the velocity of the love wave depends on its period, or you can say the frequency. So this diagram that you are seeing is taken from Stein and Weisssenbruch, and I think I have showed this picture to you in the previous lecture as well. If you look at this picture, there are three orthogonal directions, X, Y and Z, and there is a source that is located at the origin, and there is this receiver, and the direction from source to the receiver is known as the radial direction, and there is a vertical direction that is positive downward, and the perpendicular to the XZ plane is the transverse direction that is indicated by Y direction. So Rayleigh wave is predominantly consisting of P and SV wave, or you can say the P and SV wave coupled with each other to give the development of the Rayleigh wave. And the SH wave motion that is perpendicular to the XZ plane will give rise to the love wave. So the XZ plane consists of the particle motion for the P and SV wave, and the perpendicular to the screen there will be the Y direction, that is also known as the transverse direction, will be consisting of SH wave motion. Now in order to understand the love wave, we will have to consider the low velocity layer over an infinite half space. That means there is no end to the layer just beneath the layer that is above, which is of lower velocity material. So you can see in this picture there is this SH wave that is moving and getting bounce off from the surface, and then there is this boundary, or you can say that there is a contrast between low velocity layer above and the high velocity half space below, and then it is again reflecting back from this particular contrast and being basically observed at the point Q. Now you can see there is this small h term which defines the thickness of this layer, and we are considering again the orthogonal system of coordinates, that means X, Y and Z, where Z is positive downward. So if in terms of wavefront, if we see, the wavefront is traveling from here in this direction, and if we consider the harmonic wave, or you can say the sine wave or the cosine wave, there will be the multiple places over this wavefront that the phase will be same along its path. So you can see, if this path we will take, then along this path there will be the multiple points on this path, the phase of the wave will be same. So we will utilize this property in order to generate the dispersion characteristics of the love wave and see how it goes on. Now let's consider a case where the wave is such that it undergoes the constructive interference at the surface, and we will look for the condition where the phase at point A and the point Q will be same. So that means this is your point A here and this is your point Q here. So at point A and at point Q, the phase will be same, that we are going to consider. Now, in order to represent your wave equation in terms of polar equation or polar complex number equation, then we know that we can represent it as Z is equal to R e to the power iota theta, where iota is the complex number, R is the modulus of the complex number, and theta is the phase. So for a typical SH wave, we can write the displacement equation for the SH wave as U is equal to B e to the power iota in bracket omega t minus kxx minus kz. Since you know that the wave is traveling in the xz plane, but its particle motion is happening in the y direction. So the wave number will be in terms of kx and kz, and omega is the angular frequency and x and z are the coordinate, that is the coordinate directions x and z. So the phase, if we will be talking about for this particular equation of the displacement, then this phase can be represented by phi, that is basically nothing but this particular term here, that is omega t minus kxx minus kzz. This picture basically represents the coordinates, the complex number in the polar format. So, or you can say in the complex plane. So this is the phase, and here you have the modulus of the complex number r. So now we can rotate the spatial coordinates into a direction of the ray. That means consider the ray is basically traveling in this direction with the wave number k beta, because we are considering the SH wave motion. So it will be having the shear wave velocity, that is beta. And if suppose the j theta is the angle at which it is incidenting upon the interface or maybe any material, then we can rewrite this particular equation here, that is in the Cartesian coordinate system to the polar coordinate system, like this: U is equal to B e to the power iota in bracket omega t minus k beta d. So k beta is the wave number component in the direction of the ray, and d is the distance in the direction of the ray. So if we define some more relationships, then we can easily write, if suppose this angle of incident is j, then cos j will be kz divided by k beta. So that means we can write k beta, that is the term here, as in terms of the vertical wave number as kz by cos j, that is further equal to the omega by beta. Now the phase for the ray is given by phi is equal to omega t minus k beta d. So you can remember, you can see this is the phase here. So omega t minus k beta d, let me rub it and show it to you clearly. So this is the phase here, omega t minus k beta d. So this we have rewritten it, phi is equal to omega t minus k beta d. Now what is our aim? We want to examine the phase difference between the point A and Q. So if you want to write the phase at A point, this is the A point here, let me rub it here. So this is the point A here. What is the phase at A? Let's suppose the wave had started out from this particular point A. That means t is equal to 0. And if we talk about d, that is the distance in the direction of the ray, because wave is starting out at A, that means d will also be equal to 0. Now let's talk about d, let's talk about q. If we talk about the ray has traveled a distance AQ here, right? So AQ will be in the form of vector addition will be what? It will be AB plus BQ. That means AQ here can be written as BQ plus AB. So that is what we are going to do now here. So you can see, if suppose the phase difference is some multiple of 2 pi, then the wave interfering constructively. And if we suppose find out the phase at point A, that is phi A, will be equal to what? Omega t minus k beta d. That will be equal to omega t is 0 at A and t is also 0 at A, that means the phase at A will be 0. Now let's talk about point Q. So phi or the phase at Q will be what? Omega t minus k beta t. That means omega dot 0. So time is again 0 at t, and that means minus k beta AB plus BQ. That means we have rewritten D, that means the AQ as AB plus BQ, as I told you previously. Now we need to basically consider one more factor here. If you look at this particular diagram here, the wave is going down and then reflecting back. So there will be additional phase difference will be there because of the reflection. And that additional phase difference will be nothing but it will be 2 tan inverse mu2 r beta 2 star by mu1 beta 1 2. So that is basically happening because of the reflection at the interface between the layer and the half space. So you have seen this particular term in the previous class as well when we were deriving the equation for the love wave. In order for the love wave to basically exist at the interface, so in order for the Rayleigh wave to exist at the interface, so what we have done, we have basically considered that the wave's amplitude is decaying with respect to depth. In order to have that condition to be true, to hold true, we defined that the phase difference will be equal to 2 tan inverse mu2 r beta is beta 2 star divided by mu1 r beta 1. So basically when we have the total phase difference between A and Q, that will be k beta in bracket AB plus BQ, k beta AB plus BQ plus this much of phase difference. So this much of phase difference, and if the wave is interfering constructively, that should be equal to a multiple of 2 and pi. So using some trigonometric substitution, what we can do, we can write AB and BQ in terms of cos J, cos of incident angle. So if you look at this particular figure again, then what you can observe here, this entire angle here, if we suppose the angle of incident was J, then this entire angle will be 2J, right? So you can write the equation for cos 2J, that will be equal to what? That will be AB divided by BQ, right? So you can write AB here, you can write AB is equal to BQ cos 2J. So BQ cos 2J, let me rewrite it. This is your BQ cos 2J. Now similarly, you can write BQ. So if suppose you are considering this triangle, then you can write BQ as well. So what is BQ? BQ is equal to, so this angle is how much? This is J. So you can write BQ is equal to H upon cos J, because cos J is what? Cos J is this particular term, that is H, and divided by BQ. So BQ is what? H upon cos J. So BQ, if I want to write this BQ, if I want to write AQ, if I want to write AQ, that is how much? This AQ will be what? AB plus BQ. So AB is what? BQ cos 2J plus BQ. So BQ we know what we are. So now if we take BQ common, then what you will be left with? 1 plus cos of 2J. Right. So BQ is what? H upon cos J. And this entire thing will be 2 cos square J. So cos J will be cancelled out. You will be left with H upon 2 cos J. Now that is what we have done. So AB plus BQ will be equal to 2H cos J, and that we can incorporate it here, and that will become this thing. So K beta is equal to minus 2H cos J plus 2 tan inverse mu 2 r beta 2 star by mu 1 r beta 1, that is 2 and pi. Now we know that from this triangle that cos of J will be what? Cos of J will be Kz divided by K beta. So that is what it is written here. And r beta is nothing but, we have discussed in the previous classes, that it is basically the ratio of vertical wave number to the horizontal wave number, that is kz by kx. When we incorporate this into this previous equation here, we can rewrite cos j, and so we can rewrite this cos j here. If we write cos j is equal to kz by k beta will be cancelled out. You will be left with kx. Now kx r beta h plus tan inverse mu 2 r beta 2 star divided by mu 1 r beta 1 is equal to n pi. That 2 has come here and then cancelled out with each other. And finally what you will be left with, you will be left with this. Right. So what we are doing here, we are taking the tan of the both of the sides, and you will be having this expression in the end. So now you know that the multiple of n pi will be 0 in case of tan. So this particular term will become 0. Now what you will be left with is mu 2 r beta 2 star divided by mu 1 r beta 1 is equal to tan in bracket kx r beta h. So now we can write in terms of r beta and kx. So you know that r beta can be rewritten as cx square by beta square minus 1 to the power under root, and kx can be written as omega by cx. Now when we incorporate that, you can get this particular equation. Okay, so if you look at this equation, this is basically a transcendental equation, which means that it cannot be solved algebraically, but you can solve it graphically. So for the tan, this particular term, in order for the tan to have realistic solutions, realistic roots, this particular term inside tan should be greater than 0. So when we do so, then what you will get cx square by beta 1 square is greater than 1. That means beta 1 is less than cx, and cx square by beta 2 square is greater than 1. That means beta 2 is greater than cx. So this particular term should, if it is a real, then it should be 1 minus cx square by beta 2 square should be greater than 1. So that will vertically give you cx is less than b2. So when you combine these two things, then you will get cx is in between beta 1 and beta 2. As I told you, if I want to solve this particular equation, we need to go and approach the graphical solution for this particular equation. So now, for this purpose, if I want to solve it graphically, I need to basically consider a new term, new parameter, that is zeta. This new parameter, zeta, is nothing but it is basically equal to this particular term. Now, when I will do that, I am sorry, it is not equal to this term, but basically you need to keep omega separate, and then whatever you will be left out, that will be equal to zeta. So this zeta will be equal to h upon cx in bracket cx square by beta 1 square minus 1 to the power under root, where cx will be varying between beta 1 and beta 2. Now let's see what is the range of zeta, what is the minimum value of zeta, and what is the maximum value of zeta. So maximum minimum value of zeta would occur only at the minimum and maximum value of the horizontal apparent velocity, that is cx. So zeta minimum will be 0 when cx is equal to beta 1, and zeta will be maximum, that will be equal to h upon in bracket 1 by beta 1 square minus 1 by beta 2 square at cx is equal to beta 2. So basically you can say the zeta will be varying in between these two minimum and the maximum values, and that is also true for the love wave to exist in the low velocity layer over a high velocity half space. So then what we can do, we can write this particular equation in terms of zeta and cx and beta. So that will be tan omega zeta is equal to mu 2 1 minus cx square by beta 2 square to the power under root divided by mu 1 in bracket h upon cx zeta. So now we are going to solve this particular equation using the graphical solution. So what we are going to do, we are going to make this tangent curve, and we are also going to make this 1 by zeta dependent curve. So you can see this is dependent upon 1 by zeta. Here is the term 1 by zeta. So 1 by zeta means you are basically drawing some hyperbolas for the right hand side, and tangential curves for the left hand side and see where the intersection of both of the curves will be happening. When you do so, wherever the interaction will be happening, that you can consider the solution of this equation. Now, let's look at the LHS. So, LHS is the tangential term, that is tan omega zeta, and that will be having the 0, that will be equal to 0 at zeta is equal to n pi by omega, right? And it will be plus and minus infinity at m zeta is equal to m pi by 2 omega, where m is varying between, where I will be having the even odd numbers, that means 1, 3, 5 and so on. So you can see these are some of the basically curves that are drawn in Stein and Weissschen book. So that is for period 5 seconds, that is for period 10 seconds, that is for period 30 seconds, right? And then you can see on the x-axis you have your parameter zeta, zeta and zeta for all the periods. And these curves are drawn for a particular parameters, physical parameters, such as beta 1 is 3.9 km per second and beta 2 is 4.6 km per second, which means that your Cx will only be varying in between 3.9 km per second to 4.6 km per second, right? Likewise, you can see the density of the low velocity layer is 2.8 gram per centimeter cube, and the density of the half space is 3.3 gram per centimeter cube, and velocity and the thickness of the low velocity layer is 40 km. So that using all these parameters, we can basically find out this particular terms here, right? So now you can see that, as I told you, the LHS, that is the tangent. So these are the tangents that we have drawn. This is one tangent, this is another tangent, this is another tangent, likewise. Okay, since our Cx is varying up to 4.6 km per second, so that is why it will be ending. So you can see this is the curve, this is the axis for Cx, where the Cx is varying from 3.9 to 4.6, right? So let's rub it everything and understand it in a much more clearer way here. So what I can show, so as I told you, the zeta is having the values, when zeta is equal to n pi by omega, the tangential curves will be 0. So these are the 0 values here, and it will be having the infinity and plus minus infinity values when zeta is equal to m pi by 2 omega, where m is the odd number. Likewise, if you look at the RHS is the hyperbolic curve, where it is depending upon 1 by zeta value, and its value will be infinite for apparent horizontal velocity when it is equal to beta 1, and at that same point the zeta will also be 0. Now this curve will decay monotonically. So you can see this is the curve which is decaying here. This is the dashed line curve here. That is the hyperbolic curve which is decaying monotonically. And you can see that its minimum value is at the Cx is equal to 3.9. That is beta 1. And its maximum value is here. Its maximum value is here. And where the apparent horizontal velocity is beta 2. That means the curve is decaying monotonically to 0. So you can see the tangent and the hyperbolic curve are basically intersecting at this point, and at this point, right? So likewise, you can see this phenomena is happening in all the curves associated with period 10 also and period 30 also, right? So what you can observe here, the first intersection, the minimum velocity, minimum horizontal velocity at which the intersection is happening is known as n is equal to 0, or you can see that the lowest value of Cx for which there is a solution is called the fundamental node, and the higher modes are represented by the solutions at n is equal to 1 and n is equal to 2. So what you can see here, in the case of 5-second period, the fundamental mode is occurring here, n is equal to 0. In case of period 10, when the period is increased, that means when it is increasing, the fundamental mode is observed here. And when period is further increased, the fundamental mode is observed somewhere here. That means as you increase the period, the apparent horizontal velocity also keep on increasing. That means the higher value of the Cx will be associated with the higher value of the period. That means what you can draw in here, you can draw this dispersion curve where you can see this is the fundamental mode dispersion curve. Here one axis is representing period, another axis is representing apparent velocity, that is Cx. So you can see for n is equal to 0, the velocity is increasing with respect to the period. Likewise, you can draw the curve for n is equal to 1 and n is equal to 2. Right. So now let us consider the effect of the wave period on the tan inverse zeta term. That means tan zeta term. That means since tan is 0 at the integral value of the pi, then zeros of tan zeta term will occur when 2 pi by t zeta is equal to n pi. Right. So this will occur when zeta is equal to nt by 2. That means if you want to see what is the difference between the two consecutive zeta values, that will be basically nothing but t by 2. Just incorporate n is equal to 1 because you want to see the difference between the two consecutive zeta values. That means zeta n plus 1 minus zeta n will be t by 2. So when wave period goes up, the amount that zeta has to change to get from 1 0 to the next increase will be t by 2. This caused the normal mode to be further apart. So you can see as you increase the period, as I told you, when the period is increasing from 5, 10, 30, as you increase the period, the difference between the two modes will also keep on increasing. That is what this equation is representing. So, and that is what it is written here. This causes the normal mode to further apart. We can also so that is what we have done here, and we have also seen the plot versus apparent velocity and the wave period, and this basically represents the phenomena of dispersion, where you have seen with period the velocity of the dispersive wave, that means the velocity of the love wave is keep on changing. That means you can see for the fundamental mode the dispersion curves look something like this. For these are the other modes of the dispersion, that is at n is equal to 1, that is n is equal to 2. Okay, so what is the thing that should be noted here? The fundamental mode velocity increases with increasing wave period, thus love waves are inherently dispersive. So what we have learned today, love waves have SH motion, they need positive velocity jump or gradient to exist and are inherently dispersive in nature. The condition for the constructive interference at the surface is given by k beta in bracket AB plus BQ plus 2 tan inverse in bracket mu2 r beta 2 star by mu1 r beta 1 is equal to 2n pi. That we should. Now when we solved this equation and we got this finally, and then we draw the curve between the tangential values and the right hand side of this equation, and what we saw, the tangential curve and the hyperbolic curve wherever they were meeting were giving basically a solution to this equation related to the modes of the dispersion. Here in this equation, this zeta is equal to h upon cx in bracket cx square by beta 1 square minus 1 to the power 1 by 2. The lowest Cx for which there is a solution is known as the fundamental mode. Higher values of Cx solutions are called higher modes or overtones. And also one thing that you must remember, the love wave exists when there is a velocity gradient, or you can have the curved surface of the earth. Okay, so that is what we have learned today, and these are the references, and thank you so much. We will be meeting in the next lecture, that is for lecture 4, module 3. Bye-bye.